Hi class, today we're going to look at section 4.4 or the laws of logarithms. So first we're going to actually just look at the laws themselves. So let A be a positive real number with A not equal to 1. Let A, B, and C be real numbers such that big A and B are greater than 0. So first, we have that log base little a of A times B, that equals log base A of A plus log base A of B. And then for 2, we have log base A of A divided by B. This is log base A of A minus log base A of B. And then third, we have log base A of A raised to the C. And this is C log base A of A. So these are our 3 big laws that we're going to be working with. So the idea behind this, for one, so recall that when you have x squared times x cubed, this equals x squared, or x to 2 plus 3, which that should be a 3. X2 plus 3, which equals x to the 5th. So this is similar for A raised to the A times A raised to the B. This will equal A raised to the A plus B. And that's why in 1, when we have the A and B multiplied, we can separate them as log of A plus log of B. That's the idea behind this. So the log function respects this behavior. And then for the second one, similarly, if we have like x to the 5th over x cubed, this will give us x5 minus 3, which equals x squared. So if we have A raised to the A over A raised to the B, this will give us A raised to the A minus B. So log also respects this behavior. And then lastly, the idea for number 3 is if we were to have x squared all raised to the 3rd, this would give us x 2 times 3, which equals x to the 6th. So if we were to have A raised to the A all raised to the C, this would equal A raised to the A times C. So that's why we have C times the log of A, log based A of A up here. Okay, oops, there we go. So now we're going to look at an example. So if we were to look at log base 4 of 2 plus log base 4 of 32, this would give us log base 4 of 64, because 2 times 32, that's 64. Or I'll actually write it as 2 times 32, which equals log to the 4th of 64. Well, log to the 4th of 64, this is the same as 4 raised to the, I believe, 4th power. Yes. And then, so here we are able to rewrite this as just 4 because we have 4 and 4. So then we just will grab this exponent here. I believe that 4 to the 4th. Let me double check that real fast. We have 4, we have 16, and then we have, nope, it's 4 to the cubed. That was my mistake. 64 is actually 4 cubed. So it equals 3. There we go. All right, and then looking at another example, if we look at log base 2 of 80, and we minus log base 2 of 5, that will give us log base 2 of 80 over 5, which is log 2 of 16. And 16 is 2 to the 4th power. And so then similarly to the one above, since we have base 2 and 2 raised to a power, that means this will just equal 4. And then for one last one, we're going to look at negative 1/3 log 8. And this will equal log, and now since I didn't write a subscript on the log, that means that we are using log base 10, but I don't need to write it since this is the common logarithm. So then here we'll bring that negative 1/3 in as our power. And so then this is log of 1 over 8 to the 1/3, which is log, and then the cubed root of 8 is 2, so it's log of 1/2. And then since we don't, this is not a clean one like the other ones, on a test you would not be required to go further, but on homework, since you can use calculators, we could approximate this as negative 0.301. And remember, this means that if we raise 10 to the negative 0.301 power, that'll give us about 1/2. Okay. Now moving on, we're going to look at expanding logarithmic expressions. So the law of logs, it lets us know, or lets us write the logarithm of products or quotients. Quotients is when you're dividing something, as sums or differences. And this process is called expanding a logarithmic expression. So when you're asked to expand something, we're referring to the process I'm about to show you. I'm going to illustrate it with an example. So expand the following expression . Okay, so first we're going to look at log base 2 of 6x. So this will look like log base 2 of 6 plus log base 2 of x. And this is nice because this is a constant number, where this is our changing function because it has our x involved. So that's one of the reasons we'd like to separate it. And then if we look at something a little different, if we look at log base 5 of x cubed y to the 6th, this will be log base 5 of x cubed plus log base 5 of y to the 6th. And then we can bring these exponents down in front. And we will end up with 3 log base 5 of x plus 6 log base 5 of y. And then if we look at one last example, if we look at the natural log of a times b over the cubed root of c. So the first step we're going to do is we're going to separate the numerator and the denominator. So that will give us the natural log of AB minus the natural log of the cubed root of C. And then here we can separate our A and B of A plus the natural log of B. And then here, this cubed root, this is the same as writing C to the 1/3. So we can pull that 1/3 out. So this will be minus 1/3 the natural log of C. And we can also reverse this process. In a process called combining. So if you are given an expanded function like this, where all of the things are separated by sums or differences, and you're asked to combine, you're going to pull it all back into one natural log term where everything inside is products and quotients. So they're processes that undo each other, the expanding and the combining. Now we're going to look at another example of combining, or a new example, but with combining. So we're going to combine the following expressions. So if we look at 3 log base 2 of x minus 1/2 log base 2 of y. So the first thing we can do is we can bring in these constants here and bring them back in as exponents. So that'll give us log base 2 of x cubed minus log base 2 of y to the 1/2. And now since we have this minus sign here, that means we can combine them in as one quotient. So we'll have log base 2 of x cubed over, and then I'm just going to rewrite this 1/2 as a square root. So the square root of y. And there we go. That's that problem combined. And now we're going to look at another example. So if we look at 3, the natural log of s plus 1/2 the natural log of t minus 4 the natural log of t squared minus 1. So the first thing we're going to do is we're going to bring in these constants back as exponents. So we will end up with the natural log of s cubed plus the natural log of t to the 1/2 minus the natural log of t squared minus 1 all raised to the 4th. And now I'm going to combine the plus term first before I combine the subtracted version. So that'll give us the natural log of s cubed times t to the 1/2 minus the natural log of t squared minus 1 all raised to the 4th. And now we can get our quotient. So this will look like the natural log of s cubed times t to the 1/2 all over t squared minus 1 to the 4th. Okay, and now this next thing is a warning, because there's a simple mistake that often gets made with logarithms. So log of x plus y, this does not equal log base a. Log a of x plus log a of y. We can't separate when you're adding something within a log. It doesn't work. Similarly, if we have log a of 6 over log a of 2, this does not equal log a of 6 over 2. Similarly, log base 2 of x, all of this cubed, this does not equal 3 log 2 of x. So when you're adding inside of a log, you can't split it up. When you're multiplying out, or when you're dividing outside of a log, you cannot divide it. And when you're, because these are two functions divided by each other, and when you're raised to a power, but it's raising the whole function log 2 of x, the whole thing raised to a power, this does not let you bring it down. You can only bring an exponent to the outside if it's the inside x cubed. All right, so now we're going to move on to an application of log. We're going to look at the law of forgetting. So if a task is learned at a performance level P naught, then after time t, the performance level, oops, that's not how you spell performance. The performance level P satisfies log P equals log P naught minus C log of t plus 1. And this is where C is a constant. That depends on the task that we are examining, and T is measured in months. Okay, so we're going to solve for P. So if we take log P equals log P naught minus C log of t plus 1. So first we can look at this number here, the C, and we can raise it, bring it inside. So this is log of P equals log of P naught minus log of t plus 1 all raised to the c. And now, since we have this subtraction sign, we can make it a quotient. So we have log of p equals log of p naught over t plus 1 all raised to the c. All right, and now we can exponentiate both sides. So since this is log base 10, what we're theoretically doing is raising both sides. We're having everything be the exponent of 10. But since log and the exponential base 10 are inverses, that will just give us p equals p naught over t plus 1 of c. And if you guys are having trouble when you're writing your t's and your plus signs, I like to, this is just a little side note, I like to make my t's have a little curly tail because that will look different than my plus signs. Rather than t plus, that will look kind of funky. So this is an unnecessary note you don't need to write down, just a helpful hint. Okay, so now we've solved for p. So now if you score a 90 on a history test, what score can you expect to get on a similar exam after 2 months? And after a year? And here we're going to assume that c equals 0.2. So we have our p naught equals 90 and our c equals 0.2 and t is measured in months. So in 2 months, whoops, not moths, months, we'll see p equals 90 over 2 plus 1 all raised to the 0.2, which is approximately a 72. And then if we look at in 1 year, oops, which is 12 months, not moths, I really want to write moths, we will have p equals 90 over 12 plus 1 all raised to the 0.2. And this is approximately a 54. Okay, so that was an application problem. And now we are going to look at the change of base formula. So if we let y equal log b of x, so this means that b raised to the y equals x. So if we look at log a of both sides, so if we look at log base a of b to the y equaling log base a of x, well, so this becomes y log a to the b equaling log a of x. And then we can have y equaling log a of x over log a of b. So, and remember our y up here is log b of x. So this lets us know how to compute y with a different base. So our change of base is simply log b of x equals log a of x over log a of b. And this is really helpful because your calculators only have log base 10 and the natural log, which is log base e. So if you need to compute a problem that's log base 6, you could do log base 10 of your number over log base 10 of 6, and that will give you the answer that you need. So that's why it's really important. And if we use an example now, so use the change of base formula to evaluate each logarithm. So for the first one, we're going to let b equal 8 and a equal 10. So if we're going to look at log base 8 of 5, that will look like log of 10 of 5 over log 10 of 8. And when you plug this into a calculator, you get 0.77398. And then if we look at a second one, so here we're going to look at we're going to use the natural log as our change of base. So if we look at log base 9 of 20, this is the natural log of 20 over the natural log of 9. And plugging this into a calculator, you get approximately 1.36342. And this is useful because your calculator only has log 10 and ln built in. So that's part of the reason we use log 10 and natural log in these problems. So yeah, thanks for listening, class. I'll see you next lecture when we are looking at the exponential and logarithmic equations.